So we're talking about magnetic fields around current still, but I want to look at the current going out of the page. And we actually have discussed this, but I just want to like slow it down and draw it again. We've got magnetic field around that wire. Just thinking about what's happening end on for this cross section of wire that's flowing towards us, because we've got current coming like this. There's our current coming out of the page at us, kind of three-dimensionally thinking. And what we said before was, according to the right-hand rule, the magnetic field is going to go up on the right and down on the left. And no, those are not letter V's. Those are the arrow orientation for the magnetic field. And if we want to color code it, let's keep it red, fine. Okay. So we've got our magnetic field. And then, a distance further away, would the magnetic field be weaker or stronger? Weaker, but it would still be up on the right and down on the left. And so we could say at that distance away, let's call it distance r, away from the current source, I could talk about the magnetic field being proportional to two things. Being proportional to the current. In other words, more current, more magnetic field. Magnetic field is also proportional. Actually, I shouldn't say proportional. I should say inversely proportional to 1 over r, because what we said earlier was that magnetic field is being spread out over a circle, not a sphere. Now, inverse proportionality is reserved for things that spread out circularly. Inverse square proportionality, 1 over r squared, is for things that spread out spherically, right? So one starts with an S, one starts with a C. They both start with a S. But together, those proportionalities say that magnetic field is going to be proportional to 1 over r. Sorry, not 1, I over r. Now, if we were to actually do some calculations on this, and we measure the magnetic field as one column, and we linearize this system, so we measure the current and the radius. We actually calculated I divided by r and populated a whole column of data with I over r, I over r, I over r for a particular current value measured at a certain distance away. Cool? Measure the magnetic field at a certain distance away. And this actually reminds me of something that like Cavendish would have done or something like this, but it wasn't him. And we end up getting a magnetic field versus I over r graph. Remember, I over r is not either I or r, it's a calculated value, okay? And this is called linearization. The reason, if this proportionality holds, the reason that we would linearize this system is because if B is truly proportional to I over r, then this graph would be a straight line. This graph actually was a straight line when people went to go do it. So I want to do like a quick little note on this. There is a coefficient that can be found as the slope of this relationship. And this really does remind me of what Cavendish did, but with gravity, right? You guys remember we talked about this once before? Linearization is really, really powerful for deriving formulas. Anyway, that slope, let's just call it a constant, but a magnetic constant, as it turns out, has a factor of 2 pi buried in it. And earlier I suggested that there's probably a 2 pi buried in it because the magnetic field gets spread out over a circle, right? 2 pi r, circumference of a circle. And then the leftover little bitsy we call mu naught. Now that mu naught value over the 2 pi, this kind of completes the coefficient, is the magnetic permeability of free space. And it describes how well magnetic fields get allowed to permeate into space, okay? Mu naught is the magnetic permeability specifically of a vacuum. And it has a value of 4 pi times 10, oh, there's pi again. It's almost like it's part of the code of the universe, times 10 to the power of negative 7 Tesla meters per amp. What a gosh darn ugly unit. All divided by 2 pi. And so whether you express this as Km equals mu naught over 2 pi or 4 pi times 10 to the power of negative 7 Tesla meters per amp over 2 pi. You guys notice that the 4 pi and the 2 pi, there's some canceling that would happen there. And so that's like a convenient little constant for the universe. Cute, eh? I bet you there's some neat little math aside that somebody out there has done on some YouTube channel about what the consequences of that are. But I'm not going to go down that rabbit hole right now. But I do think it's pretty cute that they cancel in some neat ways. And so if I was going to write code for how reality works, I think I might build that into the code. Maybe that'll be my next project. And then that means that what we said before was magnetic field was proportional to I over R. We got to complete that as an equation now. That means the magnetic field is equal to Ki over R, where that K is the K sub M that we wrote before. Or, depending on our mood and the day of the week and what we know, we might say magnetic field, is equal to mu naught over 2 pi times I over R. And so here, I'm giving you the keys to the house. You guys now know what the value of mu naught is. Okay. Now, it's always going to be written on your equation sheet or something like that. You don't have to memorize it. Don't get hung up on that. But we can just write it down here, where mu naught is equal to 4 pi times 10 to the negative 7 Tesla meters per amp. And the units all just work out. And in terms of naming this thing, it's good to have power over something by naming it. We say that mu naught is the magnetic permeability of a vacuum. Oh, and I ran out of space. Magnetic permeability of a vacuum. Okay. And of course, it's going to be different if you set up a magnet underwater or something like that. So we're going to do all of our calculations based on doing stuff in a vacuum, only because the mu value is going to change depending on the location or the environment in which we do all this stuff in. There was a question earlier about when we would ever want to know about all this magnetic stuff and the electric stuff. And hey, just as an aside, did you know that every motor is actually just a generator, but used in the opposite way? Every electric motor, that is. Not gas motors, don't get me wrong, okay? But electric motors, every electric motor is actually also, or could also be used as a generator. That's kind of a neat thing. I want to do an example, and we have just enough time for this example. If I have R equals 2.0 centimeters, and I is equal to 4.5 amps. That's actually a fair bit of current, 4.5 amps. By the way, if you ever look at the fuse box in your car, you'll probably see, how many people have ever looked in the fuse box in their cars? What's the biggest amperage you see in your car? Is it 10 amps? Oh, yeah. So I mean, like, this is a decent amount of electricity, though, right? Like, current flow is decent, 4.5 amps. Determine the magnetic field near the wire. Okay, so we're talking about the exact scenario that we have up above, where just like you might be expected to know, acceleration due to gravity is 9.81 or something like that. We would say B is equal to mu naught times, and I'm just subbing into my formula, 4.5 amps divided by 2 pi times, I wouldn't write it as 2 centimeters. What would I have to write it as? Yeah, 0.02 meters. Yeah. So 4 times 10 to the power of negative 7. So 4 pi times 10 to the power of negative 7 Tesla meters per amp times that 4.5 amps over 2 pi times 0.020. And like, this is actually one of those convenient times where you might want to cancel the 4 and the 2 and cancel the pi. And if that makes it quicker for you to do your data entry, now we're just talking about 2 times 10 to the negative 7 times 4.5 divided by 0.02. That's okay. You can do some canceling. You guys correct me if I'm wrong, but I get 4.5 times 10 to the power of negative 5 Tesla. Does that sound right? Okay.